Swayam Prabha. Digital India. Educated India.
Welcome to module 7, lecture 3. In the lecture 2 of this module, we just introduced ourselves to shrinkage of concrete, the different types of shrinkage. Namely, we talked of chemical shrinkage, plastic shrinkage, autogenous shrinkage and drying shrinkage. So, we just the terminologies associated with them and what exactly they mean, we have defined them, and then we just stated the factors influencing the shrinkage. Today, first we will look into mechanisms of shrinkage, and then we will look into factors affecting shrinkage, and then prediction of drying shrinkage. This is the most important one amongst all them, particularly in normal concrete. So, we will look into this. So, mechanism of shrinkage, like creep, it is again generally related to adsorbed or interlayer water. Like creep, it is. So, that is why they are dealt together, usually shrinkage and creep, and they have similar sort of related mechanism with respect to microstructure of concrete. Then the movement of, so this is related to adsorbed or interlayer water. Movement of this water out of the gel results in reduction in volume of CH. Movement of this water, the gel water, interlayer water out of the gel results in reduction of volume of CHS. The capillary, calcium silicate hydrates. So, it actually results in reduction in the volume of CHS gel. Now, when something is drying, when let us say capillary, drying is taking place, drying is occurring, capillary tension is set up because there is an increase in the curvature of the menisci. Capillary tension is set up because of increase in the curvature of the menisci. So, when actually water is moved out, when water moves out, the menisci curvature increases and this sets up a kind of tension. This sets up a kind of tension. This sets up a kind of tension, increases the tension in a way. The tension, it increases the tension, and this is balanced by a compression. This is balanced by a compression in the system, in the CHS skeleton, and this induced balancing compression actually causes volume change. So, this is one of the theories that capillary menisci curvature increases when water is moving out. This is well understood, there is no problem about that. Change in the menisci because of withdrawal of water. So, as the water is withdrawn from the pores, capillary menisci, curvature of the capillary menisci will increase. It is inversely proportional to actually R. So, the smaller R, smaller the R, the larger is the curvature is proportional to that. So, it increases, larger is the curvature, and that is what happens. So, that induces there is a tension increase and it has to be balanced. So, there is a kind of compression is induced in the skeleton of CHS, results in volume change or shrinkage. At lower humidity, of course, change in surface energy of the CHS due to removal of firmly water molecule, adsorbed water molecule, is thought to be responsible for reduction of volume. So, you had adsorbed water molecule, water layers, adsorbed water layer, and as you remove this. So, if you remove this one, remove adsorbed water. So, removal of adsorbed water, right, removal of adsorbed water results in change in surface energy, because this the adsorbed water was there very much, and the moment water goes away, there is a change in surface energy. Now, this results in actually forces causing kind of causing kind of pull within the material, and therefore, reduction in volume. So, this is another reason there is a collapse mechanism sort of. So, this results in adsorbed water removal can cause actually change in the volume or shrinkage. So, there is another theory. So, first one was capillary tension theory, as we said. Second one is surface energy. As we are removing the water, the surface energy changes occur, and that results in surface energy changes would occur, and that results in actually kind of change in volume or reduction in volume, and that is why shrinkage occurs. The another theory is that disjoining pressure, that of disjoining pressure. So, removal of water causes reduction in pressure and hence the volume. So, if you remove water, the disjoining pressure, pressure would be reduced, pressure which was it would reduce, the pressure would get reduced, hence the volume will reduce. So, pressure which was pushing them out, now it's got reduced. So, there will be in reduction in volume. So, pressure reduces, volume would also reduce, is that the idea, pushing out pressure is reducing. So, there is a kind of change in the volume. So, this is all, this is another theory for shrinkage, and that these are the kind of theories that has been put forward to shrinkage in nutshell. These are the kind of possible theories that has been put up. But one thing is very clear, that it is the removal of water from the interlayer that causes shrinkage, So, removal of water may be even just internal removal from gel to capillary pores, because the capillary pores itself was got emptied, or change in the reduction in volume because of the one of course, was related to chemical shrinkage, which is somewhat different. Chemical shrinkage was somewhat different, because the reaction products occupies less volume than the original volume, reactants volume. So, this is chemical shrinkage, but other cases can be associated with removal of water from the interlayer situation. So, particularly drying or similar shrinkage can be related to removal of water. So, since all these are happening, these processes are not reversible. For example, if you add water, some of the capillaries might change by this time, or some of the pores might have changed by this time because of the collapse mechanism, because of the shrinkage. The dimensions might have changed, or whatever, there may be changes, and then formation of additional breaking of some bonds, formation of additional bonds, that is possible. And because this processes phenomena, if you add water back, the pressure will not be same as what it was earlier. Similarly, the surface energy restoration, if you do by adding water back, it may not be same exactly as before. So, putting all this together, the shrinkage is not fully reversible, and this is possibly because of breaking of the bond, and possibly formation of additional bonds. So, that is what we understand about shrinkage, its mechanism sort of. But one thing is very clear, drying shrinkage is more prominent than other shrinkages in normal concrete. So, this what we talked was related to drying shrinkage, and this is prominent than other shrinkages in normal strength concrete. Autogeneous shrinkage, which we talked about in the previous lecture, this occurs in sealed specimen because of creation of empty spaces. See, originally water filled spaces, hydration reaction is occurring. So, originally water filled spaces So, this was water, this is cement. So, hydration reaction is occurring, this water gets consumed. Now, this is sealed, let us say this is all sealed, this is all sealed specimen. So, this water actually reacts and gets consumed, what is we call as self desiccation, but this leaves some voids in the space, because water filled space has gone out, the volume of the hydration product is also we know is less, and this space is not being filled up fully, and therefore, it can result in a kind of empty spaces, and that can, due to self desiccation process, even if you have sealed it, no water you are replenishing, there will be water loss in the after the skeleton has been formed, after initial set has occurred. So, empty space remains even in sealed specimen, because the water has got lost. Whatever water is still remaining was there in the sealed specimen, besides that some empty pores are created, and in this space are actually thought to be causing self desiccation. All right. So, this self desiccation or autogeneous shrinkage, self desiccation and then autogeneous shrinkage, and this autogeneous shrinkage is considered to be more prominent in low water cement ratio concrete. That means, your high strength concrete, modern day high strength concrete, autogeneous shrinkage may be more prominent than drying shrinkage. Drying shrinkage, because the in high water cement ratio concrete, there are a lot of space or interconnected permeable pores system would be there, through which water can evaporate out. So, drying is more prominent there. While in autogeneous, low water cement ratio concrete, the the permeability is not very high. So, therefore, self desiccation would cause consumption of the water, and the evaporation would not be as dominant as in normal strength concrete. So, self desiccation will result in actually creation of new empty pores, and that is thought to be causing a kind of shrinkage, as we have seen, I have defined earlier. There is a macro level dimensional change occurring in sealed specimen, and that is what we call as autogeneous shrinkage. So, they can be more in high strength concrete or low water cement ratio concrete compared to drying shrinkage. So, they are very important currently for high strength. We will see them, might get somewhat some better insight into these mechanisms, etc., when you look into also the measurement process, because measurement separating the shrinkages, different kind of shrinkages, and measuring them, we will see how we can do that. So, we will see it in the next lecture. So, at the moment up to this only. Now, then what are the factors influence, factors those influences shrinkage. Now, we just looked at them and we said that aggregate content and aggregate properties, this will be one of the major thing. Water cement ratio and time, curing condition, relative humidity, volume to surface area ratio, slump, fine aggregate to total aggregate, air content and cement content. So, all these are related to, all these are the factors. So many factors actually influences the shrinkage. So, we will see one by one. Let us see the effect of aggregate. First of all, modulus of elasticity of aggregate. Now, we can understand this, as I said, the stiffness is trying to shrink, something is trying to shrink. I have one material and the other material. So, I have one material, I have one material and the other material. This is one material, this is other material, and they are bonded and they are trying to shrink, they are trying to shrink, this is trying to shrink. So, let us say this shrinks by this amount, this shrinks by this amount. Now, paste shrinks, aggregate do not want to shrink. This is, let us say, is aggregate, this let us say is aggregate, and let us say this is paste. So, this will tend to shrink, this will tend to shrink, this will tend to shrink somewhat, but this will not shrink, because aggregate is inert and its volume change would not occur like that. So, as this will try to shrink, this will also try to bring it together, but this will then exert a net upward force to this, net upward force to this. That means, shrinkage of the paste will be restrained by aggregate. right, will be restrained by aggregate. Now, aggregate how much it will restrain? For same strain, the stress would be more if the modulus of elasticity is more. So, if this is high modulus of elasticity, this will actually share more load for the same strain, and it will be less loaded. Besides, it will actually provide that restraint more. So, modulus of elasticity has a role, modulus of elasticity has a role. So, aggregate modulus of elasticity. So, if you look at this, this is sandstone, this is shrinkage along this direction in micro strain, time in log scale, quartz. Now, quartz has got, it is very stiff. So, quartz is here, it is quartz is here, actually quartz is here, here is quartz, this is sandstone, this is limestone, this is granite, this is some gravel, this is basalt. So, it will depend upon stiffness of the aggregate itself. So, higher the modulus of elasticity, it would actually have less, shrinkage will be less, because it will restrain the shrinkage. So, shrinkage will be less. So, time in log scale along this direction, shrinkage along this direction, and different types of stones for same, all other things remaining same, and at different age shows less different shrinkage. So, stiffer one obviously will show less shrinkage in the concrete, less shrinkage in the concrete, all right, less shrinkage in the concrete, all right. So, higher modulus restrains shrinkage, that is what we are saying, higher modulus restrains shrinkage, higher modulus restrains shrinkage. Volume of aggregate, that is quantity, obviously now this is very clear, because if my is a paste which actually shrinks, aggregate does not. So, therefore, this is shown for two different water cement ratio, 0.35, this is water cement ratio 0.550. So, this is 35, these are 50, somewhat less, but you see the volumetric content of aggregate percent. So, volume percentage of aggregate, 100% aggregate obviously is not the situation, 0% aggregate. So, if the paste shrinkage is considered to be 1, this is relative shrinkage, paste shrinkage is considered to be 1, with 40% aggregate you will get possibly 40% shrinkage will get reduced by 60%, at 20% it will get about 40% reduced. So, depending upon the volume content of the aggregate, shrinkage would get reduced. More volume means less shrinkage, more volume means less shrinkage. Of course, when you look into the effect of shrinkage, but this we are talking of the shrinkage in the system itself, There is a case where you have actually very low volume of aggregate, shrinkage in the overall system could be lower, or shrinkage cracking could be lower. We will talk about that sometime later on. So, volume same aspects, more the volume, because aggregate do not shrink, therefore, more the volume, less will be the overall shrinkage. So, higher aggregate content, lesser is shrinkage, higher the aggregate content, lesser is the shrinkage. Okay. Now, one can look into a simple empirical equation. This is the shrinkage of concrete, it can be related to shrinkage of paste into 1 minus g to the power n, where g stands for aggregate content, n stands for a value of 1.7. So, it is a kind of you can say square, because this is fitting, try to fit an empirical equation. So, S sort of S c by S p is 1 minus g to the power n, where g is the aggregate content. It is a nonlinear curve. So, one can actually relate to this one. So, n is roughly about 1.7, n is equals to 1.7. So, this is an empirical equation. So, we can understand that more the aggregate content, lesser will be the, because this is aggregate content. So, more the aggregate content, lesser is the shrinkage. Water cement ratio, let us see water cement ratio. So, this is we are plotting against water cement ratio, and this is the shrinkage. Now, volumetric content of aggregate percent. This line is for 50% aggregate, 50, this is for 60, this is 70 and this is 80. So, if you see 80%, aggregate is 80%, shrinkage will be lower, but as my water cement ratio increases, shrinkage increases. Water cement ratio increases, shrinkage increases. This we are talking mostly of the drying shrinkage. We are talking of normal strength concrete, not very low water cement ratio situation. So, we are not going below 0.3, it is only up to 3 we are talking about. We are so we are looking at normal strength concrete, not very high strength concrete, where it is autogeneous shrinkage which actually governs, which can be more than the drying shrinkage. So, this is essentially we are looking at drying shrinkage for normal strength concrete. So, you see, as the water cement ratio increases, shrinkage increases in all cases, in all cases shrinkage increases as water cement ratio increases. Now, water cement ratio, increase in water cement ratio obviously would mean more capillary pores in the system, and which drying out, it is related to drying out, can easily dry out. So, this is higher the water cement ratio, it has a tendency to exhibit higher shrinkage, but absolute cement content has also got a role, because paste content itself, if it is high, shrinkage will be more. So, this has got higher paste content, this has got less paste content. In other words, water cement ratio is one issue, but paste content is also an important issue. Now, paste content means it is sum total of water plus cement. So, water plus cement. So, water plus cement divided by you can 1 and 3.15 specific. So, this is the volume of water plus cement. So, paste volume will be this, paste volume will be this. We are not talking of pozzolanic cement or anything of that kind. If that is there, that will also add to the paste. So, this divided by total volume obviously will give us relative paste content, total relative paste content, and if this is high, my shrinkage is higher. Shrinkage is higher because paste is what shrinks, aggregates do not shrink. All right. And in this one again, if the water to cement ratio is high, so higher W by C, higher W by C, higher W by C, shrinkage is more, higher shrinkage is more shrinkage is higher. So, for a given paste content, shrinkage increases with water cement ratio. For a given paste content, shrinkage increases with water cement ratio, because a large amount of capillary pores, there is a possibility of more drying is possible, more water may move out, and even with larger capillaries, the scope of emptying the gel pore or interlayer water movement in the capillary space is now more. So, this is related to those aspects, this is related to those aspects. So, this was water cement ratio and of course, volume of aggregate. Then relative humidity and age. So, if this is age, we have seen earlier also, with age shrinkage increases. We have seen that earlier also, with age shrinkage increases, right, with age shrinkage increases, and in this case of course, there is a reduction if you have 100% relative humidity, which means that you will have some amount of swelling. So, this is 0 and this is 100% relative humidity, in fact, you will have swelling. So, this is swelling, actually this will be swelling, but if you have lesser 70%, 50%, so if you have lesser, shrinkage goes on increasing, but then it tends to be somewhat flattening out in the long run. It has a tendency to flatten out in the long run. All right. So, this is time and relative humidity. So, if it is fully saturated, there could be swelling. If the relative humidity is very high, close to 100% or just 90% or so, shrinkage will be very little, but it is all related to drying. So, one can understand when you have 50% relative humidity in the surrounding, which means the drying would occur, drying would occur by evaporation. So, capillary water will get out by evaporation, and as capillary tends to become dry, interlayer water will move out from gel pores, gel water will move out from gel pores to the capillary pores, and as we have said, drying mechanism involves movement of this water out, the shrinkage would actually occur. So, this is understandable, right. Now, volume to surface area ratio, volume to surface area ratio, it is almost similar to the situation of creep again, volume to surface, but volume to surface area ratio. So, if you have higher volume to surface area ratio, volume to surface area ratio. So, this is the volume is here, volume, and surface area is the peripheral surface area, in this case. So, this is the surface area, this is important. Now, surface area, volume to surface area ratio, if it is large, which means that I have got lesser surface area per unit volume, lesser surface area per unit volume. So, I will have less evaporation. So, when volume to surface area ratio is small, I will have more evaporation. So, more evaporation. For example, if this volume to surface area ratio, this is S, this is S. So, V by S, more S per unit volume means more evaporation. So, less S per unit volume means less evaporation. In other words, V by S increases, I will have less evaporation. So, therefore, for gravel aggregate and sandstone aggregate, shrinkage, ultimate shrinkage, that is long term shrinkage, because we have seen that shrinkage actually is a function of time. Therefore, one should talk about shrinkage at different ages, So, ultimate shrinkage is final, infinity, at infinite time, and it is seen that it depends upon the volume to surface area ratio. We are talking again of drying shrinkage, not the other shrinkage, just which are less dominant. So, we are talking of drying shrinkages at the moment more, which is more for normal strength concrete. We will discuss something about autogeneous shrinkage later on when we talk about measurements and so on and so forth. So, drying shrinkage is what we are concentrating on right now, and if you have large surface area, less volume per unit volume, or more volume per unit surface area, then shrinkage will be less. So, evaporation is less. So, this is what it is. So, you can see that this is a function of, it is related to evaporation loss, right. So, loss of water decreases with volume to surface area ratio, with increase in volume to surface area ratio. That is the idea. So, we will come to prediction of drying shrinkage, but remember we did not talk of some of the factors, namely slump, aggregate fine to coarse aggregate ratio, etc., because we did not discuss this. Let us just go back to that slides quickly. Let us go back to that slide quickly go back to that slide and see what are the things we did not really look into, account for. You see, we did not talk of slide, slump, fine to total, air content, cement content. Now, this is indirectly covered actually. Slump is there as a factor in the ACI formula, it is there. A flowing concrete or less flowing concrete has something to do with the water content, and cement content has something to do with the paste content. Air content would create some more voids in the system, and fine aggregate to total aggregate ratio, because total aggregate has got a role, it will be shrinking less compared to fine. So, this other factors are there, rest all we have actually discussed. So, let us now look at the prediction of shrinkage, like we did prediction of creep, and similarly ACI formula and the British formula we will look into. So, roughly some idea wise, 14 to 35% of 20 years creep occurs in 2 weeks, and 40 to 80% occurs in 3 months, and 60 to 85% in 1 year. So, if you look at 3 months or so, majority of the actual shrinkage occurs in this. So, all the problem related to shrinkage, like cracking if there is any, drying shrinkage cracks if they come very quite early in the life of the structure, within 3-4 months, maximum 6 months. Usually it is 2-3 months, 2-3 months the cracks come, right. Not you do not see them very long, so rarely 1 year or so. So, mostly it comes pretty early. So, therefore, this is important. Now, method appropriate to normal weight concrete is ACI 209R method. You can estimate using this, and that is what we will try to do. That is what we will try to do. And then of course, the British BACN system would be there, and we will discuss that as well. So, what it says, shrinkage at any time when drying has started from T 0 would be given as S alpha, which is the ultimate shrinkage. This is given by this formula. So, shrinkage S T tau 0, this should be tau T 0, tau 0 at time T days measured from start of drying at T 0, tau 0 days. So, this is measured at time T days measured from start of drying. So, drying start from tau 0 time, and shrinkage is given. So, where this is infinity and related to the time. So, it is a kind of hyperbolic equation. As you can see that as this time increases, this time will increase, this will increase, but there is a 35 added there, 35 added there. So, how higher this would tend to, actually this will tend to a constant value, that is ultimate. So, it gets related to a fraction, right. So, when this is very large, this value will be small compared to this, right. This is in days, this is in days, actually these are all in days. So, this is also in days. So, if you have something like large value of this one, this will be nearly 1. So, as infinity is, that is how we are defining. So, ultimate shrinkage for moist curing. But if it is any other condition, the formula will change, any other condition, formula will change. So, this is for steam curing, this value is 55, for steam curing this value is 55, this value is 55. In other words, the shrinkage is initial early days, when this is small, shrinkage is relatively lesser. This is small, let us say this value is small, shrinkage will be relatively lesser, because shrinkage will be relatively less, shrinkage will be relatively less, shrinkage will be less, because this value is higher, this value is higher. So, for steam curing, it's the ultimate shrinkage is related to the shrinkage at any time. So, shrinkage at any time t, shrinkage at any time t when drying has started from tau 0 is related to ultimate shrinkage, is related to ultimate shrinkage, all right. And now, ultimate shrinkage you can find out ACI method, ACI method 209 method actually tells you the procedure to find it, all right. So, S ultimate shrinkage is given by this formula 780 into 10 to the power minus 6 K 1 dash, K 2 dash, K 3 dash, K 4 dash, K 5 dash, K 6 dash and K 7 dash. So, like the Cribb formula had 7 such factors K 1, K 2, K 3, K 4, K 5, K 6 if you recollect, depending upon curing condition, then volume to surface area ratio, slump, etc., etc. If you remember aggregate coarse to fine ratio and all that. Here there are such 7 factors. Here there are such 7 factors, and here there are some 7 factors, and each factors are related to the relevant property. For example, K 1 for steam curing, K 1 for steam curing, for steam curing 1 to 3 days and for 7 days for moist curing. So, for K 1 is equals to 1 for steam curing 1 to 3 days, and so it is for related to curing condition. K 1 dash prime is related to curing condition. So, it is 1 for if you have done steam curing for 1 to 3 days and 7 days if it is moist curing. So, it is actually the concrete condition. We are talking of normal concrete again, and this is largely related to drying shrinkage prediction. This is largely related to drying shrinkage prediction. So, if you do steam curing, for 1 to 3 days or moist curing for 7 days, the K 1 could be taken as 1. So, that is the datum. For other cases, you can actually find out from this table. For example, moist curing 1 to 3 days, this is 7 day we have said is 1, and this factor, if you have less curing, this value increases, if you have more curing, this value reduces. Similar values are available for steam curing also. So, this is you can use simply K 1 equals to K1 equals to 1, 1.2 depending upon number of days the curing has been done. So, part of the table has been reproduced, for the purpose of understanding and getting familiar with the procedure. So, K1 dash factor is related to curing. The table for steam curing is separate, or the way to find out is given, and that is given in the committee report ACI 209. I have just reproduced the normal moist curing scenario only. K2 dash is humidity coefficient. This is exposure condition. So, this is 1.40 minus 01 H, where H stands is relative humidity, where your relative humidity is 40 to 80%, and this value is different if your humidity is more than 100%. In fact, this will be much less, as one can see. 30 K2 factor would be 82 H relative humidity, 82. So, this formula is given this. For example, you take, let us say 40% relative humidity. So, K2 dash would be equals to 1.40 minus 0.01 into 40. So, which would be simply 1.40 minus how much it would be, 0.4. 1% of 40 is 0.4, 0.04, 0.4. 1% of 40 would be 0.4. So, this is simply 1. And if it is 80 in this formula, let us put it. So, 300 minus 0.03 into, let us say 0.8 or 80. So, this should be this is for 80. You can find out from this formula also. So, from this formula, if I find out, I get 3 minus 80 into 0.03. So, this would be 2.4, which is 0.6. And if I put in this formula 1.40 into 80, let us say, just rub this off, this I am just rubbing off. So, this is 80 and 80 is 1.4 minus 0.8, which will be 0.6 again. So, from both the formula you get it because here the multiplying factor is more, right. So, this value is more, but this multiplying factor is more. For example, if you have 100, then this will be simply 0. If you put H is equals to 100, then it is simply 0. So, actually there is no shrinkage if it is 100% relative humidity. So, this is a factor related to relative humidity. This is a factor related to relative humidity. Now, volume to surface area ratio, K3 depends on the member volume to surface area ratio, and this is a part of the table. If it is 12.5, it is 1.35. We said that surface area more means more evaporation. So, as this increases, there will be reduction and this reduces. So, 37.5 has been taken as a base case, and if it is less than that, then you will have more values. So, K3 dash depends upon volume to surface area ratio, right, volume to surface area ratio. So, for any other values other than 37.5 is given by this kind of formulae. For example, if it is more than 37.5, but less than 95, then the formula is given as 1.23 minus 0.006 V by S, and T minus T 0 less than 1 year. If this is more than 1 year, for these cases the formula is given 0.006 is fine, but this is 1.17. So, this basically depending upon the age. So, if it is less than 1 year, the value is something like this. If it is more than 1 year, the value is something like this, and if it is more than 95 centimeter, this is given by this formula for V s greater than. So, it is 1.2 exponential of 0.00473 V by S. So, the curves that we gave earlier, we discussed earlier, it is related to those curves, right. So, that is how we find out the volume to surface area ratio. K4 is related to slump. More the slump, K4 is more, which means my ultimate shrinkage will be more. So, S is the slump. So, 0.0024264 S slump in mm. So, for 100 mm or 100 more the slump, more are likely to. In fact, it is talking in terms of the water content of the system. So, more the slump, more is a shrinkage. You can look into K5, we can look into K5. K5 is related to fines to coarse aggregate ratio. So, equations are given again, if the fine to coarse total aggregate content is less than 50%, in other words, if my fine content in the concrete is less than 50%, all right. So, equation is here. So, if this is more, if more fines are there, more shrinkage, if lesser fines are there, less shrinkage, because coarse aggregate is the one which will actually restrict the shrinkage, restrict the shrinkage. So, more fines in the system, you are likely to have more shrinkage, and if this is more than 50%, fine is very high, this value is relatively less, 0.90, but this value is higher. So, two empirical formula is given, is a depending upon the fine content of the system, right, depending upon fine content of the system. So, K5 is related to cement content, and higher the cement content, K6 is related to cement content, higher the cement content, more will be the shrinkage, because paste will increase, and this is given in kg per meter cube. And K7 is related to air content, because air content means more void, and therefore, it is related to higher the air content, higher will be the drying shrinkage. So, what we have seen, there are 7 factors through which you actually you can predict the shrinkage. Number 1 factor, K1 prime, was related to curing. So, for the datum is taken as 1 to 3 days of steam curing or 7 days of moist curing, which is a standard practice. So, if you are curing less than that, you will have higher value of K1. If it is more than that, then you will have lesser value of K1. So, it depends upon curing condition. K2 depends upon, K2 depends upon, K2 depends upon, K2 depends upon, K3 is related to volume to surface area ratio, K2 depends upon humidity condition. So, K2 depends upon humidity condition, K3 depends upon member volume to surface area ratio, and K4 depends upon slump, K5 depends upon fine aggregate content, and 6 depends upon the cement content, and 7 depends upon the air content of the system. So, there are these 7 factors, and it is pretty easy to calculate from this formula, knowing all those factors, and you can estimate the ultimate shrinkage and shrinkage at any other state. For example, at any other time when you have actually started drying at tau 0 can be related by the first 2 formulae that I have given. So, therefore, you can predict the shrinkage at any time using this formula that is given in the 290 R. British method of course gives 2 cases, 6 months and ultimate, that is 30 years shrinkage and swelling, and it gives you in a kind of a nomogram like we had one. So, in British method what you do? Actually it is determined from figure, of course, a nomogram for 190 liter per meter cube of water. For other water contents, the proportional shrinkage values are calculated. Equations are available for estimation of swelling and shrinkage. So, like we talked about the creep, in case of creep there was a nomogram, here also there is a nomogram, and you can estimate the swelling and shrinkage from the 6 month or 30 years ultimate shrinkage, which we will see from the nomogram you can obtain it. But the this method of course is referring to a nomogram. It is also slightly less elaborate, because you can see the factors that it takes into account, while the ACI method of course is definitely more elaborate, taking as many factors as possible, 7 factors as we have seen, and it is easy to implement in a Microsoft Excel or some such sort of a spreadsheet or similar sort of thing. So, it is easy to actually utilize the method. So, their first formula is S T and T is in tau 0, is S 28 days, 100 3.61 ln t minus tau minus tau 0 minus 12.05 to the power half. So, what you want to know at any time you want to find out with drying starting from tau 0, any time you want to find out with drying starting from this date. First you have to find out S 28 and then you can relate this. Now, S 28 can be obtained from 6 months or ultimate shrinkage by formulae which are available. Let us see the case of this nomogram. This nomogram, as you can see, it will be relative humidity RH along this axis. So, it varies from 20 to 100 and this is the average humidity in United Kingdom condition, this is the average humidity in average relative humidity inside in UK, but elsewhere it could be different. So, this side is shrinkage, this is swelling. So, the value of shrinkage here is 0, y axis gives you ultimate shrinkage, right, ultimate shrinkage, and this gives you, that is 30 years shrinkage, and this side, this portion gives you 6 months shrinkage, and which can be related to 28 days shrinkage, right. So, it is related to relative humidity, one factor that is taken into account, and the age factor, there are 2 age it is given. So, ultimate and basically ultimate and 6 months shrinkage, whichever you want, and they can be related to 28 and then at any age you can find out. Now, this is volume to surface area ratio in millimeter or in inch in bracket. So, for 75 millimeter volume to surface area ratio and 150 and 300, and here again 75, 150 and 300. So, what is happening? This 300 is this scale. So, supposing I have a relative humidity, let us say is 60%. So, I go here and I know my volume to surface area ratio is 150. So, I will come to this scale and it will be close to 300 into 10 to the power minus 6 for 6 months, and if I am to get for ultimate shrinkage for the same relative humidity, then I would go for, this is for 150, this is volume to surface area ratio. So, this is ultimate 300, 6 months will be somewhere here, which is about 80. So, for 60% relative humidity, if I have a volume to surface area ratio is close to 150, I will have 300 microstrains after 30 years, while I will have about 80 microstrains after 6 months. Now, anything anywhere in between, you can, for example, this scale, this is graduated. So, if you have volume to surface area ratio say 145, sorry, this is this is graduated from microstrain 145, then you have to actually interpolate between these two. You can determine for 75 and determine from 150 and then possibly and then for 300 also, but they are not linearly varying. While this is 450, this is 400, along this line this will be 400, less than 400, and this will be much less than 350. So, one can even plot a curve with 3 points and then interpolate. So, some kind of interpolation is possible, but this you can see is relatively less elaborate. Besides, it is less elaborate. Besides, actually graphs are really cumbersome these days. So, what you have on this scale is relative humidity 20 to 100. This curve is there which you can use in this nomogram. Here the for ultimate crepe 3 volume to surface area ratios are given, and from this curve you can arrive at the ultimate shrinkage, knowing the volume to surface area ratio that you are working on. For 6 months shrinkage, you are on this side. So, therefore, what we see is that both this method can predict the shrinkage. So, let us summarize this then. To summarize this, essentially what we have looked into? We have looked into mechanisms of shrinkage today, and we have explained fully that it is how it is related to interlayer movement of interlayer water, and the theories those are available. We have put them forward, and we have understood that it cannot be reversible. But you see this, when you have more than one theories, it is not very easy to come out with a generalized mathematical formulation. So, therefore, you have empirical formulas of prediction of this one. So, we have seen on what does it vary, what does it vary actually, what are the factors on which it vary. We looked into mechanism, then we looked into factors on what it varies, and then the prediction as per various course, that is what we do. So, factors, major factors that we have seen of course is relative humidity, curing condition, relative humidity condition, volume to surface area ratio, and fine aggregate content in the total aggregate system, slump, air content, etc. Now, some of those factors and aggregate, of course, the aggregate type we have seen. So, what are the basically factors which affect that we have seen, and then we have seen the predicting formulae, and we have also understood that it is possibly easier to predict through the ACI method rather than the British method which is existing. Right. So, the next thing that we will be discussing in the next class is the measurement of shrinkage. Now, one, the Leach-Ateliers methods were used for measurement of shrinkage of paste conventionally, and other is the chemical shrinkage. So, some modern methods are there, that is what we will look into, and then potential of shrinkage cracks that can occur, that is what we shall be looking into in the next class. Right. So, with that actually we will conclude our discussion today. Thank you.